This is Ronaldo's movement. It mimicked Kobe Bryant's action, but looks a bit awkward. Proudly, this is the Do You Know Club's apartment dance. Hello everyone, this is Error. Utilizing NVIDIA's robotics platform, Carnegie Mellon University has created humanoid robots that can mimic the actions of famous personalities. The technology you're seeing here is named ASAP, which stands for Aligning Simulation and Real-World Physics, not as soon as possible. It was released under this name. Now you can see Ronaldo celebrating with his signature gesture, C. In this method, reinforcement learning is used to achieve much more precise movements compared to traditional methods. Recently, Figure AI announced a partnership with OpenAI, aiming to push forward with their comprehensive robot technology. Meanwhile, Tesla's humanoid robot is generating a lot of excitement. However, since this implementation differs from that of the robot, NVIDIA is now actively distributing their robot platform to various areas. At the same time, this platform can simulate and experiment, so it's getting attention. Let's take a look. See how naturally and agilely it moves. This is a slow-motion playback of Ronaldo's celebration move. It also imitates Kobe Bryant's move, but it looks a bit awkward. I'm not sure if Kobe actually did it this way, but it still feels a bit awkward. In the case of LeBron James, his movements wouldn't be so wobbly, which is a bit disappointing. Next, the robot's execution of a side jump and its swift lateral movement are quite well represented. Moving forward, kicking to the right, these actions were previously challenging for Boston Dynamics to accomplish using hydraulic actuators for parkour movements. However, our esteemed Do You Know Club's apartment dance appears somewhat slow, showcasing various facets of this technology. The effectiveness of ASAP fine-tuning can really be seen when it comes to kicking with one foot. Without it, the robot struggles, but with ASAP applied, it significantly enhances the kicking range. LeBron James's movements, even small ones, are well captured. So, what is different from existing tech? How is it different from Tesla's method? What does NVIDIA use? And where is this robot from? These are things you might be curious about, right? Naturally, ASAP employs a different approach compared to Tesla. The movements that the robot learns in the simulation go through a two-step training process to accurately and delicately replicate real-world actions. As you can see, it's watching a video of someone moving. Here, Ronaldo is celebrating. After watching how basketball players execute these moves, they assess the pose and estimate the best method to replicate it. Then, they proceed to train the robot to imitate these movements accurately. The actual paper compares traditional methods during simulation. The traditional methods include SysID, which stands for System Identification, and Delta Dynamics. When comparing ASAP, this snapshot might not show much. First, you need to know the traditional method, right? This robot has specific physical properties. This process involves precisely measuring the actuators, the friction levels, and the support dynamics. Next, we simulate the robot's behavior in a virtual environment. The key objective is to replicate the real-world environment as accurately as possible within this simulated world. This method is known as SysID Delta Dynamics, however, focuses on tracking the differences between the real world and the simulation, and making the necessary adjustments to bridge these gaps. This technique is extensively utilized in the field of robotics. In practice, kinematics with multiple actuator freedoms is the goal. PD and PID control decide the manipulator's end position. These are learned in robotics. During control time, differences can arise between the simulation and the real environment. Delta Dynamics corrects these differences by continuously bridging the residual error gap. This reduces errors and trains the model to accurately replicate simulated actions in the real environment. This method has been widely used. Ultimately, what is the goal? There are two main approaches. One is designing the model itself to follow the actions the robot performs in simulation or what it sees through cameras, and the other is bridging the gap between simulation and real-world actions. Specifically, with Delta Dynamics, it is important to learn through reinforcement learning in simulation, but also to use real data effectively. Collecting and correcting that error is also important, so this ASAP method should indeed be called delta action. It's also called delta state. We refer to it as delta action when adjusting the policy learned in simulation to fit the real environment. The existing Delta Dynamics technology compensates for the state referred to as delta or gap. So, if there's an error in the simulation, it compensates right away. For example, if the robot jumps 1 meter, it needs to reach 3 meters, but it only reached 0.8 meters. So, there's 0.2 meters left. This method corrects that part. It focuses on state changes. The Delta Action ASAP approach allows us to see the expanded dimensions of the difference in actions. It's not just about comparing the difference between specific states, but rather adjusting the overall gap in actions. For example, if the robot was supposed to jump 1 meter, but only managed 0.8 meters, the Delta Action approach corrects this by adjusting the motor output, or the overall movement itself, allowing for more fundamental alignment. This can be seen as a part of the process, so the Delta Action model is trained first. Using pre-training to track motion means capturing Ronaldo's actions on video. Then, this needs to be converted into robot motion. We transform this and use reinforcement learning to train the simulation. So, for actions like jumping or breathing, we start by transforming and closely tracking these movements. Next, we enter the fine-tuning phase, where the system already understands the basic motion patterns. As the real robot performs these actions, we collect data on its actual movements. This allows us to correct any discrepancies between the simulation and the real-world robot movements. The aim is to correct that delta based on actions and behaviors. The overall framework is fundamentally based on the IsaacSim concept, which is a recurring theme throughout the paper. Here, we also mention IsaacSim, which refers to NVIDIA's second-generation simulation technology. They offer multiple platforms for simulating and building robots, right? Among these, IsaacGym is known for creating a physics simulation environment based on NVIDIA GPUs. This is achieved through reinforcement learning. When the robot performs actions like jumping or moving sideways, it supports real-time learning in simulation. Then, ASAP, which simulates a near real-world environment, allows the robot to learn in real time within the simulation, as mentioned earlier. The outcomes of the training are assessed in real-world settings. So, even if there's no physical robot, the evaluation can be conducted within the Isaac simulation environment. Think of it like working out in a virtual gym, which is a fun analogy. Essentially, it's quite similar to DeepSeek in structure, as it involves pre-training on delta actions beforehand, akin to how an athlete prepares before a major event. After pre-training, we proceed with fine-tuning. How do we do fine-tuning? Through reinforcement learning. However, during the initial training, reinforcement learning is applied to both the delta and the policy. In the case of DeepSeek R1, it uses the V3 base model, which is trained to generate a variety of chains and prompts through R1.0, and these are then integrated. Using that, it enhances performance with reinforcement learning. The ASAP method also tracks motion using reinforcement learning. But to be precise, pre-training and reinforcement learning are not unique concepts. They have different methods. Pre-training is like Twitch's approach, while reinforcement learning is like a generator's. It finds rewards on its own, so it's seen as more creative. Deep Scout secures basic performance with the base model, then needs fine-tuning through reinforcement learning. The ASAP method leverages reinforcement learning to correct the discrepancies between simulated and real-world physics, owing to the inherent differences in robot movements. So, just because we bring up reinforcement learning here, it doesn't mean it's a one-size-fits-all solution. When you look at the comments, there are actually various approaches in the humanoid robot field. The goals pursued by Tesla and Figure AI are somewhat different from the ASAP method here. For Tesla robots, the focus is on building robust hardware and enabling real-time control to perform desired actions efficiently. They aim to create robots that can autonomously adapt to their environment based on these capabilities. This allows robots to seamlessly replace humans in factories and be integrated into home appliances. ASAP involves capturing specific actions, such as recording videos of LeBron James or Cristiano Ronaldo, or even mimicking someone performing a task, and then executing these actions in the real world exactly as they were simulated. You can think of it this way. The goals are somewhat different, so there's no need to compare their actions directly. If we consider how this technology can be applied, as robots continue to evolve to perform natural, precise, and agile movements like humans in real-world settings, it will eventually become possible for them to flawlessly mimic human actions. Healthcare robots could be employed for therapeutic treatments or other similar tasks. Instead of making autonomous decisions, these robots can execute specific, repetitive actions based on human instructions with great precision. They could also handle simple service tasks efficiently. Today, I have put together a summary of some fascinating movements. I shared this video on Instagram before our discussion today, so some of you might have already seen it. I regularly share entertaining clips and brief updates, so be sure to stay tuned for more information. This has been Era,